two, one, giver.
Hello, hello, hello. Welcome to another edition of the Tutor Wizard. Sunday edition, I guess it is today, day number 2 of a review for statistics 151, 161. In other words, basically first semester statistics, just about anywhere. Now, yesterday I spent about an hour talking about some definitions and a few other things, and I promised that today we would do some. Oh, the peanut gallery's coming by.
Why all the things were deleted?
Computations.
Why they were all deleted off my thing?
Anyway.
The cat was sleeping on the laptop the other day, so somehow she deleted all of the.
By the way, we're rolling.
I know. I figured as much.
It's all right.
I was a bit
And
jerked
if you
out.
haven't figured it out, chaos
We've
is
had coffee.
the. We're at number. What's a good? We're at 137 Chaos Lane. Send the mail to 1/137 Chaos Lane. That's that's the magic number. Yeah.
Are we fine tuning?
Yeah. Cosmic constant, I think it was. The cosmological constant. 1 over 137?
Seems
Yeah.
to prop up quite a bit.
Okay, so what's the plan of the day today? So the plan of the day is computations, of course. We're going to do that. I'm going to look at some two-sample stuff for proportions and mean values. That should eat up an hour easily. Let's talk a little bit about the level of significance first. We're going to do that. If you're wondering about, I missed some of this stuff, I want to review it again, we'll be archiving again on YouTube. Our Patreon little project continues to stymie because, software issues. The whole point we're trying to do is do streams simultaneously, which requires some configuration on Open Broadcast System, OBS. And, to make a long story short, it's Windows. And anybody who uses Linux would say, yes, we understand it's Windows, and that's why it sucks. Anyway, we'll get it sorted out.
The good one.
We'll get it sorted out.
We're working on it, which means Lorenzo is working.
That's true. The Peanut Gallery is working on it. Peanut Gallery Technical Services.
The useful one of the 3.
Let's talk about level of significance before we start with this stuff.
I laugh because it's true.
So, level of significance is indicated in notation by the Greek letter alpha.
Alpha.
And typically is 5%, but it can be anything you want. I mean, if you want, you can have it at 10%, and if you want, it could be at 1%, or any number you want, really. And of course, the question then becomes, why do we bounce around like this? So if we think about what the definition of level of significance is, or one of the ways to interpret it, I guess. I shouldn't say the definition. That's not what I really meant. What I really meant is, how do we interpret level of significance? Typically, we consider it in terms of what's the chance of a type 1 error. A type 1 error is a false positive. So now we're getting in. You'll notice that when I really want you to remember something, I slow right down and talk really slow. And then I also get really close to the camera, So I said a flashback from one of the Alfred Hitchcock movie, but anyway, neither here nor there. So the point is, if it's a type 1 error, you have a false positive. And this is the kind of, again, a lot of this is contextual, but generally speaking, a type 1 error then is when you take your study, you got your sample data, you analyze it, you come up with a result, and it says, I have found a significant result. Something is unexpectedly different. And hey, great, I get to write a paper, grant money flows, or whatever the context happens to be in your own personal circumstance. But it turns out you're wrong. And usually you're wrong because of a systematic error, but not always. Sometimes you have what's known as a statistical blip. Sometimes I refer to that as random sampling variability, is what you can attribute that to. Another way of saying luck, really. Because your samples are drawn randomly, occasionally you're going to get a very unusual sample, and that can generate a significant result when you analyze it. So when we set the level of significance, what we're really doing is we're setting a threshold for what we're willing to accept as the risk of that happening. So at 5%, 5% is just another way of saying one chance out of 20. XKCD has a good cartoon comic online explaining this. If you would do a online search for XKCD and level of significance or type 1 error, you'll find it right away. It's been around for 15, probably closer to 20 years, I would think. It's been around a long time. So sometimes what I like to do to explain some of these things is I'm going to relate a story about why we have to consider the context of the question when we set a level of significance, and then we'll do a couple of examples on interpretation of it. So I'm paraphrasing a study now from an old textbook that did a good example about why this matters and why we need to think about the context of what we're doing, whether we want to be careful about a type 1 error or a type 2 error. Now, a type 2 error is a false negative. So a false negative is when you say, well, my study didn't produce significant result. And again, due to random sampling variability, there actually is a significant result hiding in the data. You just didn't detect it for reasons. And you miss an opportunity. So if you consider how thermal electric power plants work, what they do is you use some fuel source, could be nuclear, could be coal, could be gas, could be whatever. It's not hydro, mind, because we're generating heat. So you use heat from fuel to generate high pressure steam. Steam drives the turbine, spins the turbine, generates electricity, and you get to have all your little toys that go blinky blinky. But of course, you have all this waste heat. What are you going to do? Because you just don't dump the steam into the atmosphere. The steam you see from a power plant has got nothing to do with the steam that drives the turbines. That's evaporative cooling going on. So what you do is you run the steam through a condenser. A condenser is a series of tubes inside a larger series of tubes. It's all a series of tubes. That's an internet meme. You can look that one up too. It's a series of tubes. Anyway, the point is you circulate cold water around the steam pipes, and that cools the steam back to water, and you can run the water back through the power generation system. But now you put the heat into the cooling water, and the cooling water's got to be discharged, which is why you find power plants on bodies of water, on the shore of bodies of water or rivers, things like that, because you have to dump the heat someplace. So for Edmonton, Wabamun is west of the city. There's a big power plant there, and you're always dumping. Well, that's the source of cooling water. So here's the thing. If your job is to monitor the temperature of the water being dumped back into the lake, and keep in mind, if the water being dumped back in the lake is too hot, you're going to damage the ecosystem. So it's important that the water, when it's put back in the lake, is under a certain temperature. I'm just going to say 40 degrees Celsius. I'm just pulling that number out of the air. So your job is at random times to go and sample the temperature at the outlet. So you sample and you get 44 degrees. Okay, now that's a significant difference. So what are the consequences of a significant difference where the temperature is too hot? Well, undoubtedly, there's going to be an investigation. A fine might be leveled to the power plant. Some engineers will spend time trying to fix a problem that perhaps doesn't exist. Or does exist. They don't know until they start tinkering, right? So if it turns out that the mistake was made, maybe your measuring system was uncalibrated for some reason, or maybe that was just a little blip of hot water that came out coincidentally at the time you were testing, but generally speaking, the water being discharged into the lake is at a cool enough temperature that it's not going to damage things. That's a false positive. Now, what are the consequences of a false positive reading? Well, like I said, the consequences of a true positive means the plant gets fined, engineers work, etc., etc. But if you were to detect the fact that it was a false positive, you can always give the plant back its money. And so the engineers worked some overtime. I'm sure they're not going to complain about it because they got paid for it. So, pardon me. So let's consider the consequences of a false negative then. So again, you're doing water sampling, and it turns out that all the temperature readings are indicated to be below the threshold. But it turns out, again, through either just bad luck, random sampling variability, or uncalibrated machinery, that the water is actually too hot. Well, what are the consequences of a false negative? Well, in this context, the false negative means you're going to keep pumping water that's too hot into the lake and continuing to damage the ecosystem until the next sampling where you actually detect it. So in the case of the water going into the lake story I've just related, the false negative is the more harmful of the two. Now, every problem is going to be different. You have to ask yourself, well, what's the consequences of false positive or false negative? And you adjust your level of significance accordingly to minimize that. Now, I've already told you far more than this course is ever going to ask you about, but you should understand the necessity of giving some thought to what the level of significance represents. If you take more stats, you'll run into this time and time again. Okay, so what I said I was going to do was talk about how to interpret some numbers. So let's say our level of significance is 5%, and our p-value after some computations turns out to be 0.015. Well, whenever the p-value is less than the level of significance, less than or equal to the level of significance, we say we have evidence to reject the null hypothesis. That's great. But what does this mean? So remember that 5% is 1 out of 20. Well, then what is 0.015? Well, this is 15 chances out of 1,000. Well, we can reduce this to about 3 chances out of 3. What the heck is this divided by? I'm dividing by 5, you dum-dum. That would be 3 chances in 200. Well, if you consider that there's roughly 250 working days in a year, this 200 working days represents about 8 months. So there's 3 chances out of 200 that this result that you had, that generated this p-value, occurred simply due to random sampling variability. That's pretty slim odds. This is why we say it's highly significant. Now, conversely, let's say we had a p-value of 0. I don't know, let's use a number that I know how to use. Let's say 0.20. So this is 1 chance in 5. Well, this is an insignificant result because the p-value is larger than the level of significance. And a result that can happen 1 time out of 5, just due to luck, there's nothing significant about that. It's an insignificant result, and we would say we have no evidence to reject the null hypothesis. That's the general idea. This stuff makes more sense the more you work with it. Don't try to become fluent and comfortable with all the implications of significance overnight. You have to do some of this stuff and think about your results. And after a while, it does start to make sense. Okay, I'm not going to beat this topic up anymore. Just keep in mind, for the exam, the level of significance is your chance of a type 1 error, a false positive. And if you think about it in terms of 1 out of 5, or 3 out of 200, or 1 out of 20, sometimes that's an easier way to think about things instead of trying to always deal with decimals. Okay, enough of this stuff. Let's do some examples here. Now, I did do a little bit of pre-computation before showtime today, but some of it we're going to have to wing it, which is why we have the calculator today, my good old trusty TI, which has all of it built in. I don't need to wing it. Well, there's some fun to be had when you're winging it all the time. So let's start with some proportions. So I'm not going to probably put too much in the way of context with these questions. We're just going to do the math. Here's how to do it. Because that's, at this point in time, that's what you need to know, is how to do it when you write the exam. Okay, I don't have my glasses on, but I have them with me. We'll wing it. Okay, let's say. So we have 2 samples. Sample number 1, x is 20, and n is 30. And for sample number 2, x is 25, and n is 75. And I want to ask the question, is there a significant difference between the respective proportions? Now I said, is there a difference? When the question is worded as, is there a difference? It's non-directional. So this means when we write the hypothesis, write down the alternative hypothesis, we'll use the does not equals sign. Let's do that first. So the null hypothesis is always that the proportions are different. Yeah, and I do know you're going to say, well, wait a minute, those numbers aren't the same. Of course not. When we ask if something's the same or not, we're asking, is it significantly different from being more or less equal or not? They're never going to be exactly the same. So what we write is P1 minus P2 is not equal to 0. For the alternative hypothesis, I'll set the level of significance at 5%. Now when we have a two-tailed test, and that's what this is, we have to remember at the very end to multiply the p-value by 2. So let's make a note about that so I don't forget. P-value times 2. All right. Now we can get down and calculate some numbers. Well, the first thing we need is, what are the measured proportions? What are the p-hats? So p-hat for the first sample is going to be x over n, 20 over 30. So p-hat number 1 is 0.67. I'm not going to chase more than a couple of decimals around today because, well, I'm working with a small board and I don't want to. I'm holding the chalk after all. Now, what over here? We have p-hat number 2, 25 over 75, and that is 1/3. So we'll write it as 0.33. There we go. Now on your formula sheet, when you look for the formula to do this computation, you're going to see the reference that we need p-hat pooled. Some formula sheets call it the combined, but the point is we need to have a weighted average of the two proportions. And on your formula sheet, they'll show you how to do that. I'm going to do it explicitly and I point a couple things out on how you can keep a watch for any mistakes. It's not a guaranteed always going to find a mistake if you do it wrong, but it helps. All right, so our formula we need to use, and this will be a Z test because it's proportions. Z is going to be p-hat 1 minus p-hat 2. And in the denominator, we're going to have p-hat pooled. I'm just going to use the subscript p on that for pooled. And then we need 1 minus p-hat pooled. And then we have 1 over n1 plus 1 over n2. And this is all under a square root. So just to list that out. So the Z formula is a rational expression. In the numerator, it's the difference of the measured p-hats, in other words, the measured proportions from your samples. The denominator is a square root, and under the square root, we have the combined or the pooled p-hat, the pooled proportion, times 1 minus the pooled proportion, and then that result is multiplied by 1 over n1 plus 1 over n sub 2. So there's you have to pay attention to your order of operations here, because of the presence of that bracket under the square root. Okay, let's get this pooled proportion stuff of which I speak. So p-hat sub p. Now when they give you the counts, like I have here, this is easy. Your formula for this is a rational expression, so that means you're going to have x sub 1 plus x sub 2 in the numerator. So remember, those are the success counts. In the denominator will be the total sample size counts. So the denominator is n sub 1 plus n sub 2. So if we put our numbers in here, and I'm going to make it fit here one way or the other, x1 is 20, x2 is 25, so that gives us 45 in the numerator. Our sample is 30 plus 75 for 105. So that means p hat sub p will be whatever this reduces to, which is, well, this is what I have kind of written down, so we're going to steal that. Now, I believe it's 0.4286, but you know what, I'm going to double check that with my calculator, because nobody wants a wrong answer when you're studying for an exam. So if you have a calculator handy, feel free to check yourself. How are we doing here? We got a couple people online today. Greetings to you. In fact, one of those is probably Caden. I hope it's Caden. Hi, Caden. And we also, I'm hoping Abby and Shay are joining us online today, too. Remember, this stuff will be archived. If you miss it, you can still watch it after the fact on Twitch, or you can watch it after the fact on YouTube. Just go to the Tutor Wizard channels. So I have to sort out 45 over 105. 45 divided by 105. And it is the 4286. Okay, so that's about 3/7, I'm pretty sure. All right, so this is going to be 0.4286. Well, that is the value of p hat sub p. Now, like I said, in the interest of keeping our sanity here, I was going to truncate that to 2 decimals, but you know what, I'll work with this one since we already have it in 4 decimals. I need to know what 1 minus that is. So 1 minus p hat sub p should be 0.5714, he said, minus 5714. There we go. 0.5714. Okay, we have the numbers we need now. Okay, we don't need Mr. Calculator for another moment or 6, so we'll put that over there. So let's write out this denominator now so we can figure this thing out. So, well, actually, we'll do the whole thing. So here we have z is equal to. Now we need the measured difference. So remember, p hat sub 1 was 0.67. That's here. P hat sub 2 is 0.33. So we should have a measured difference then of 0.34. I'll put that in the numerator. And it's negative, by the way. Don't lose your signs. That will make a big difference when we go to the Z table. Now, what do we have downstairs? We need 0.4286 times 0.5714. This is all under the square root, remember. Now, we also have to multiply that by 1 over sample 1, which is 30, and 1 over sample 2, which was 75. Like I said, this is all under a root, so it's going to be a bit of a computation. So have a care with that. Negative 0.34 in the numerator. Now, if you'll humor me, I'm just going to put the denominator all together in one computation and see what we get. You know, I do like to do this stuff in my head just to, scare people, but I'm not doing this one. Not today, peeps, not today. So we have that, 0.5714 times 0.4286. So if you're multiplying p hat pooled, 1 minus p hat pooled, you should get 0.2449. Now we have to multiply it by the sum of the 2 sample sizes. So be careful with your brackets or you will be wrong. 1 divided by 20. What am I saying? 1 divided by 24. It's 1 divided by 30. Pardon me. Let's try that again. Plus 1 divided by 75. So our denominator, so this is the denominator before the square root, should be 0.0114 to 4 decimals. So let's take a square root of that. And we get, pardon me, it is the chalk dust. I think it's starting to get to everybody. 0.1069. There we go. Now, yeah, it is definitely the chalk dust, I think. Okay, well, I need to make some room here, so let's scrub some of this stuff out of the way. Okay, so this is, we haven't got our Z-score yet. Z will be the division of negative 0.34 divided by 0.1069. So you get negative 3.18. So that is the Z-score. Now, of course, we have to go to a Z table to get the p-value, but here's a perfect opportunity to throw in, well, what does Z represent? Well, Z represents the number of standard deviations your result is away from the expected or the mean value. So remember, the expected difference was 0. That's in the null hypothesis. But our difference was 0.34, or 34 percentage points smaller than 0. And that is highly significant. Usually when you start looking at a Z-score around 3, magnitude of 3, you are definitely significant. So what's the p-value for this? So the p-value, I wrote it out after already multiplying by 2 to be 0.0018. So essentially 1/5 of a percentage point. So highly unlikely. That's like 18 chances out of 10,000. That didn't happen by luck. That happened because there's a significant difference. Now my calculator has the tables built in, so I'm just going to double check everything because sometimes mistakes just happen to keep rolling on. You know how it is. I don't think I've ever gotten an A on an exam in my life because I work fast, I read fast, and I make dumb errors. But, you know, that's how you do math. You make dumb errors, you learn, you move on. Okay, let's go over here. Menu. 5 for probability, and we want distributions, which is number 5. And I want the cumulative distribution for Z, which is number 2. We have that, and negative 3.18. And the p-value is a ridiculously small value, which I'm going to times by 2. And, oh, good thing I checked that. See, when I did the calculation with the calculator, it uses all 9 decimals, and that's where the p-value of 0018 came from. But I rounded this to only 2 decimals, so to be in sync with what your Z table will give you, my p-value when multiplied by 2 is 0.0014. Actually, I should round that to 1.5. So the p-value, 2 times the p-value is 0.0015, and I rounded that up from a 4. Not that it matters, because when we compare this to the level of significance 5%, it's pretty obvious that this is much smaller than this. And so we conclude by saying that there is evidence to reject the null hypothesis. Now they may ask you for the $5 explanation for this. And the $5 explanation, they may say, well, what's the distribution of the test statistic under the null hypothesis? So you would say, well, my test statistic is Z is equal to negative 3.18, giving a corresponding p-value of 0.0015 on the two-tailed test. And this being significantly smaller than the level of significance gives us strong evidence to reject the null hypothesis. That's the $5 way of saying that. But I prefer the 25-cent way of saying it. We reject, move on. Okay, so why don't we do the same set of numbers, and now we'll do the confidence interval. And we should get a similar result. Well, frankly, if they don't match, then we've done something wrong. As long as I choose the confidence level to be appropriate, they have to match up. Okay, let's do that. Now, we'll keep this. We've got to get rid of these. Now, so let's write the formula out. This is also on your formula sheet. So if you're using the formula sheet that I'm familiar with, the one at the University of Alberta, these will be on page 3. There's a table of parts of the formula. You have to put the parts together, unfortunately. So for the hypothesis test, it was the standard error part that was referenced by H null, and then there's an arrow pointing towards the square root that I showed you. Now for the confidence interval, it'll say CI, and an arrow pointing to the square root. So the confidence interval then is going to be the formula p hat sub 1 minus p hat sub 2 plus or minus. We need a critical number on z. Remember, that's a table lookup. We don't need to memorize it. I mean, I know what my numbers are, but you don't need to memorize this stuff. Now, we're going to have p hat sub 1, and this is all under the root, mind you. There's, under the square root is the sum of two rational expressions. So p hat sub 1 then times bracket 1 minus p hat sub 1 over n sub 1. And then we're going to have another rational expression, which is p hat sub 2 times, open a bracket, 1 minus p hat sub 2 over n sub 2. And that is our standard error. Now, what confidence level should we do with this thing here? So we had a two-tailed test, alpha at 5%. So we should have, we're going to use 95%. So the critical number from the Z table or the T table, I would suggest you use the T table. Most T tables have them at the bottom. Look for the infinity row on your T table. But you see, the thing is, as the sample size increases, the T distribution converges or becomes identical to the Z distribution. So at infinity, we're saying that if you let the sample get larger and larger, essentially there's no difference between the two tables. The difference is really present, though, when you have a under 100 count. Okay, so we have 1.96 for the critical number. Now remember, we knew from our earlier work that the difference between these was negative 0.34. And plus or minus 1.96, that's our critical number. And now we're going to fill out this square root. Now, this is where using 2 decimals is a real lifesaver on a small chalkboard like this, because I don't have to try and wedge all that in there. Because remember, 4 decimals on here, yeah, no, that wouldn't work at all. All right, so if this is 0.67, so p hat sub 1 is 0.67. So 1 minus is 0.33. So we're going to multiply 0.67 times 0.33, and that's divided by the sample size of 30. Now we're going to add another rational expression, which is going to be the same thing except for p hat sub 2, and that was 0.33. Wow, look at that, symmetrical. I didn't plan that, you know, it just worked out that way. 33 times 0.67, and this is over 75. That makes a big difference. Okay, so now the rest of this is calculator work, also known as pointless busy work. Okay, grabbing the button box. I did work this out ahead of time, but I thought, nah, we'll do it live. Okay, what do we got? We're going to open a square root. We're going to open a bracket. Pardon me, we're going to open a rational expression first. So 0.67 times 0.33 over 30. Plus, open a new rational expression. Same numerator. In this case, this is just pure luck, by the way. Ooh, I missed the decimal on that. That would cause a major problem. The denominator, however, at 75 count on that one will make a big difference. So if you're working this out separately, your square root should evaluate to 0.1016. Okay? I've got to multiply that by 1.96, and this will give us our total margin of error, which is 0.199. The hell is that? Ah, another 9. So 0.1991. Okay. Now, oftentimes in statistics, I'm going to need this again, in the media, you will oftentimes hear survey results reported, and if you think about it, they're reporting a confidence interval. I could say that, let's say this was a survey of people's opinions on something, and people in one city said something, agreed to a question, people in another city agreed to the same question. So we could say the difference between, say, Calgary and Edmonton was 34 percentage points, with a margin of error of 19.91 percentage points. And since this is a 95% confidence interval, we would say we were 95% confident about that. That's one way this gets reported. But for what we have to do on the exam, we need a lower bound and an upper bound. Now, so that means we're going to take the estimated difference, subtract the margin of error for the lower bound, and then we'll do the same, but we'll add the margin of error for the upper bound. So clearly, we're going to be negative everywhere. What do we have? Negative 0.34 minus 0.1991. So negative 5391. Negative 0.5. That's a 5391. That's for the lower bound. And now we'll do the upper bound. Try that again. There we go. So negative 1409. So negative 0.1409. There it is. So that is the upper and lower bound for this. And now we have to talk about how to interpret this, because quite often that's what they're going to ask you. How do we interpret this? So, in a similar manner to what we were just chatting about, that piece of chalk is done. We can say that the estimated difference between sample 1 and sample 2 is negative 0.34, or 34 percentage points, depending on what you're talking about. Giving a lower bound of negative 0.5391 and an upper bound of negative 1409. Now, we can say, actually that's not how I really wanted to say that. Let me try that again. So oftentimes what we want to say when we report this, we can say is, with 95% confidence, we have evidence that the true value of the difference between the two samples lies between negative 0.5391 and negative 0.1409. Any number in that interval is equally valid to be the value, the true value of the parameter. We can't know what it is, but we can estimate it, and the estimate puts, this is a bound on the estimate. So the thing to keep in mind for a lot of this stuff, especially on the exam, you want to try to optimize the amount of material you want to memorize. You'll notice that if this was on a number line, the hypothesized difference of 0 is not inside the interval. The interval is entirely less than 0. And when in the context of a two-sample test, the hypothesized 0 lies outside the interval, that is always evidence to reject the null hypothesis. If 0 is inside the interval, then you fail to reject the null. Because, and no, by the way, I'm not almost done.
You got a phone call.
Who?
You got a phone call. I don't know who it is.
Okay, well, first off, hold on.
I'm just kidding. I wanted to show them. Wait.
This is a telephone. The only thing about this telephone that is not completely old-timey is it has buttons.
Let me do it.
No.
Oh, they can see the guts inside.
Well, yeah.
But it says my grandma's phone number, 46400.
And this is in good Edmonton telephone orange. Yeah. This is an antique. And you know what? In a previous career, having to deal with the public, I slammed one of these things so hard that it never worked again. And
that's what the ring. Wait, that's what the ringer sounds like.
Yeah. Yes, today is show and tell. Yeah, I don't much like. I have limited patience for foolish people.
The funny thing is, you were old enough to be like, "Who is it?" When I handed it to you, you thought someone was on the other end of the line.
Those things are very robustly engineered, but if you hit them hard enough, buttons don't work anymore. And you gotta just wail on that thing. But you know what? If anybody's ever, well, I'm sure most students who are having to work retail, you understand that customers aren't always right. Sometimes they're not always human. And sometimes the best remedy for that is, well, you know, application of force. Okay, let's not go there because this is statistics, so you get a good job where you don't have to deal with customers, and that would be great. That can be very sympathetic. Okay, so this is how to do the two sample proportions test and confidence interval. Now we're going to do my least favorite, the two sample mean values test. And the reason I say it's my least favorite is for pooled comparisons, or for pooled standard deviations. The denominator is a monstrous beast, and it's error prone. But it's going to be on the exam, and, well, if you got to do it, I got to do it. So let's do it. Okay, let's clear the board. You know, on the topic of funny stories about destroying telephones because you are really, really angry, I also sent one to the great beyond, but it was one of these phones that had a lot of buttons on it for different lines, and it was a very important phone. So in the middle of a shift when no one was around, I had to go to the kitchen, get a butter knife, unscrew the wiring harness on the bottom, swap the broken phone out for one that works, change all the button labels over, put it all back together with a butter knife because all the tools were locked up. And no one ever knew. So, yeah. There's more to that story, but I'm not sharing that because I'm pretty sure you don't want to know. Yeah, maybe. We'll see. Okay, let's put some numbers up here. So again, the hypothesis for two sample tests dealing with mean values is still the same. We're going to be comparing two mean values. We are wanting to know if they're equal or not. Now, what does this business of equality represent? This hasn't been talked about too much. I know I haven't talked about it too much, but we used to beat this up quite a bit. When you're comparing two samples, the question you're kind of asking is, are they from the same populations or not? Because if they're from the same population, they should have the same mean value, the same centered mean value. Remember, we talked about this yesterday when we were doing the properties of the sampling distribution for mean values. So if the samples are significantly the same, that means they probably come from the same population. In other words, there's no real difference there. They'll have the same center, they'll have roughly the same spread. And the alternative hypothesis can be interpreted then as that they're not from the same population. You know, sometimes I used to do an example about so Edmonton has a big river that runs through the middle, and it's a swift-moving river. So basically the river isolates the north half of the city from the south half of the city when it comes to, say, things like squirrels. We have a lot of squirrels in Edmonton. So you would think then that breeding of squirrels on the north side is going to be somewhat diverse, evolutionarily speaking. The squirrels on the north side get inbred. The squirrels on the south side get inbred. Oh, I'm talking about inbreeding, and all the peanut gallery got quiet over here.
Inbred squirrels, that's all I heard.
And it made you stop, I know. He heard me talking about inbred squirrels, which I'm sure will work into a differential equation somewhere. Population dynamics.
There is one actually on red squirrels and gray squirrels mating in England because of shifting.
Are you saying that in the microphone so everybody can hear that?
Nope.
Please. So you want to repeat that?
Yeah, I guess I'll turn my mic on.
Yeah,
Right.
okay. Here comes the peanut gallery.
Yeah, so there's a population of squirrels in England, of gray squirrels and red squirrels that have hybridized and bred together because of shifting geographic regions, probably due to shifting climate patterns or something. I forget the exact reason why, but yeah, you can model all that sort of thing, which is something that we are working on tentatively. But yes, there you go. That was my 2 cents.
Oh, awesome. So we are talking population dynamics. How is your genetics changing when you keep getting together with your cousins? I didn't say it was bad. Not for me to judge, you know. And this is coming from a man with a lot of cousins. However, I haven't seen any of them in a long time. I'm kind of sad about that. It would be nice to chat with them every now and then, but I moved away from most of them. And, let's just say that my genetics aren't being mixed back into the same swimming pool. Okay, I thought I had a visual on that. That's supposed to be funny. They didn't even get it over there. It's fine, whatever. Okay, let's put some numbers on the board. We're going to compare these two. So we have two samples. Sample number 1 has a mean value, so y bar sub 1 is 20. S sub 1 is 4. And n sub 1 is 25. Sample number 2 is y bar sub 2 is, where did it go? 30. There we go. S sub 2 is 9, and n sub 2 is 36. And the astute amongst you will notice that my use of numbers involves a lot of perfect squares, because I like to keep my stuff simple. Now, let's do a one-tail test on this one. We did the two-tail test on the previous example, so this one we're going to do the... Let me just check my clock. Holy mackerel, I'm really running this out here, aren't I? That's okay. I hope you don't mind. It's statistics after all, and you got an exam to write, so more the better, right? Okay, so the hypothesis is, the null says, are these things from the same population? Mu1 minus mu2 is equal to 0. So just to be clear about this, one of the reasons we write it like that, I could have written mu1 is equal to mu2. And technically, there's probably nothing wrong with that, except it hides the hypothesized value of 0. So if we algebraically move mu sub 2 to the left-hand side of the equal sign, this is how we get mu1 minus mu2 is equal to 0. Now, the alternative is mu1 minus mu2. Now, this one's 30, that's bigger, and this is 20. I am going to set this up as a less than 0. So we don't have to chase a negative sign around. So this is what I'm doing. And why is it negative? Because 30 is a bigger number than 20. So I'm asking, is there evidence that the magnitude of the second sample mean is significantly larger than the magnitude of the first sample's mean? And if it is, I'll have a negative number, hence the less than 0. We'll use 5% again for the level of significance because there's no point in being fancy pants. Now here's the next thing. How do I know which type of t-test to use here? Remember, it's mean values. We have sample standard deviation. We're not going to do anything with z. This has to be done with t. And how we're going to do this is either going to be with a pooled standard deviation or non-pooled. And the way you check is to look at the sample standard deviations. You divide the big one by the little one. If the ratio is less than 2, you use pooled. If it's 2 or larger, you use non-pooled. Well, it's pretty obvious here that 9 divided by 4 is greater than 2. So we're going to use non-pooled standard deviation, which is much quicker, far less work, but I will do the pooled version as well. But you know what I think I'll do, in the interest of saving time and my sanity, is when I do the confidence interval, I'll use the pooled standard deviation and show you how that works out, because it's the same computation as if I did the pooled t-test with our hypothesis test. Okay, what's our formula? Our formula is t, difference of means, so y bar sub 1 minus y bar sub 2, and the denominator is one simple square root with two rational expressions under there. So the first rational expression is s sub 1 squared over n sub 1 plus, the second rational expression is s sub 2 squared over n sub 2. And that looks a great deal like the preceding confidence interval for proportions, the same structure. And I believe this is on the formula sheet now. I noticed that reviewing the formula sheet here a couple of days ago that they have included these on there. Not just on page 3, it's always been there, but it's also included with the properties of sampling distributions. Let's put the numbers in. We'll get to degrees of freedom in a moment. So y bar number 1 was 20, and y bar number 2 was 30. Okay, we got that. Now, what's our denominator? Let's start by making a square root. And our first standard deviation, S sub 1 is 4, which we have to square. So 4 squared is 16. We're dividing by 25. Ooh, look at that. Perfect square is being divided. Yes. This is why I chose the numbers I did. For the second sample, S sub 2 is 9, which we square to 81. And the denominator, the sample size, is 36. So let's get the test statistic on this. Do I have room here? Yeah, I can make this fit. So we'll go over here, equals. So the numerator is -10, which we expect, remember, because up here the alternative hypothesis is a negative sign, right? It's negative, it's less than 0, so this thing makes sense. Now what about this denominator? So, yeah, I'm not going to do that in my head. I would take a shot at it if I had unlimited time, but we want to keep this rolling on because 25 times 36 should be 900. And then we're going to have 16 times 36 and 25. Yeah, no, we'll use the calculator. But yeah, 25 times 36 should be 900. Anybody want to call me wrong on that? Let's find out. 25 times 36. Oh, look, 900. How did I know that? Here's a trick. Instead of 25, if this was 0.25, this would be a quarter. What's a quarter of 36? 9. Oh, but I moved the decimal 2 places, so I got to multiply them back on there. So instead of 9, it's 900. You don't need a calculator, people. Well, sometimes. What is that silence from over there? Are you looking at squirrel porn again? Well, you were talking about inbred squirrels. The squirrel porn. Hey, we could have a nightclub. We could have squirrel girls. Nobody? Nothing? Okay.
I gotta get that cricket.
Yeah, you need a cricket thing, a cricket sound effect. Sorry, every now and then I like to take a trip off into the weeds, if for no other reason to see who's actually awake. Oh, look, someone checked out. Probably didn't like my joke. Okay, sorry. I know. Shut up, do the math. I get it, I get it. So we have... turn the calculator back on because I spent all that time. 16 divided by 25 plus 81 divided by 36 gives us that. So if you're doing the roots, that simplify, or I haven't done the root yet, but if you're working on the material under the root, you should get 289 over 100, and we need the square root of that, which is 1.7 actually, and that one I should have known because 289 is a perfect square. 17 squared. That's 289. I should have eyeballed that. How bad. Okay, so we get 1.7. That comes from moving the decimals around a little bit. So 1.7. So here the numerator is -10. The denominator is less than 2. So we know the test statistic is going to be bigger than 5, and it'll have a negative sign on it. So we can say t is equal to -5 point something something. So 5, that's 8.5, 15. So it's going to be 5 and what, 15/17? Maybe? I don't know. Let's see. 10 divided by 1.7, and we get 5.882, which I'll bet is 15 over 17. Ooh, I was right about that. How about that? Now, what are the degrees of freedom? Because we can't estimate the p-value yet without degrees of freedom. So when you're doing the non-pooled test, the degrees of freedom is going to be the smaller of the 2 samples minus 1. So I'm going to write the min of n1 minus 1, comma n2 minus 1. That's on your formula sheet, by the way. It's on page 3 in the midst of the tables with all the parts of the formulas, and it's in the far right column. It says reference distribution. Well, I don't need a table to know that on 24 degrees of freedom, that the p-value for this is ridiculously small. So typically we would say the p-value here is greater than 0, because it'll never be exactly 0, and is less than 0.005. And if you really want, I'll see if I can get an approximate value for the p-value here, because I can always do a lookup on here. You know, most people have a TI-83 or an 84. This is a fancier one than that. But one of the reasons you're not allowed to use them is a lot of this stuff, including the distribution of t-tables and z-tables, it's in your calculator, you know. You just never bothered to learn how to find it, but it's in there. So let's go over here. Menu 5, distributions is 5, and I need the cumulative distribution for test statistic t. And what do we have? Negative 5 point, I said 88. We'll just use 88 on 24 degrees of freedom. And our p-value is 2.29 times 10 to the negative 6. So ridiculously small. But as far as what the t-table gives you, this is the last column in the t-table. So all we can say is whatever the heck our p-value actually is, it's smaller than 1/2 of 1%. So this is literally 1 chance in 200 of this being a false positive. Unlikely to be the case. So that's how to do the non-pooled 2-sample t hypothesis test. Now, I'm about an hour into this trip. I still want to do the confidence interval, and I'm going to do the confidence interval using pooled test statistic, pooled standard deviation, sorry. And then we'll turn Adrian loose, so that's just fair warning for him to get warmed up over there. You're on deck. Oh, look. My coffee cup is empty. I'll have to do something about that. Okay, let's get some of this out of the way, and we'll put the formula up here. Did you say you were going to go visit the squirrels? Yeah. All right. You have to do what to whom now?
Real world problems,
not stats? You're not saying stats isn't real world? Peanut Gallery is throwing nothing but shade. All right, let's set this up. So we're going to have y bar 1 minus y bar 2. We need a critical number from the t-table. We'll look that one up. So that's a table lookup. Remember, the degrees of freedom for pooled is different than the degrees of freedom from non-pooled. So we're not going to go to row 24 on the t-table. The way to do it is the sum of the two sample sizes minus 2. So this adds up to 41, 61, so we need 59 degrees of freedom. And what's interesting about that is 59 is not on your t-table. When the degrees of freedom you need are not on the t-table, round it down. The value I'm going to pick is going to be for 50 degrees of freedom. And I can't quite remember if that's on the table or not, but I'm going to use my calculator to get 50 degrees of freedom's critical number. So that's how I'm going to work this one out. If you have to go down to something smaller like 45, your answers will be slightly different. Not terribly though, just a little bit. Now we need 2 square roots. The first one's a beast. So it's a rational expression where we have in the numerator n1 minus 1, so that's n sub 1 minus 1, times s sub 1 squared, plus, bracket again, n sub 2 minus 1, close your bracket, multiply that by s sub 2 squared. The denominator is n1 plus n2 minus 2. This is where you get your degrees of freedom from, by the way. You can close your square root and then open another square root, which will be 1 over n1 plus 1 over n2. So that's a lot of work. If you're not handy with the calculator, I would suggest you carefully work out the 2 square roots separately and then bring them together, simply to avoid traumatic errors. Okay, so the difference was negative 10. Now I got to get that critical number. Let me find that. Now, here was where we have to use the inverse distribution for t. Of course, that's what the calculator calls it. You're just going to use the t table. So I'm using row 50. You will use whatever is appropriate, either 50 or 45 or 40, but remember, always round down for that sort of thing. 5 distributions is 5. I need inverse t. There we go. I'm doing 95% confidence, and that means the area under the curve is that on 5, 0. So it's going to be 2.009. I think that one is on the table. Seems familiar to me. So our critical number is 2.009. Now, what about this first square root? So sample size 1 is 25, so we're going to write 24, multiplied by the variance. Remember, s squared is variance, so that's going to be 16. Then we're going to have 35, that's n1 minus, or n2 minus 1, times the square, the variance is 81, and the denominator is 59. And then over here we're going to have 1 over 25 and 1 over 36. So just to reiterate, if you're just trying to write this down, so the entire margin of error then is the critical number 2.009 multiplied by the square root of a rational expression 24 times 16 plus 35 times 81, and that's all divided by 59. That's the first square root. The second square root is 1 divided by 25 plus 1 divided by 36. That's under a square root, so you need to root that at the end, and then when you multiply those three things together, we get the margin of error. So I'm just going to do that all in one shot because the peanut gallery is getting antsy, and that means they're getting passive-aggressive. Uh-oh, my spidey sense is tingling. Or is it my squirrel sense? I don't know, it's one or the other. Now, what do we got going on here? 2.009 times, now what the heck is this going to be? This is a mess. This is what this is. 24 times 16, I should know that. 480, I think. No, that's not right. It'd be, no, it's a bit more than that. 504, I think. It's got to end in a 4. Yeah, but it's 504. 24 times 16 plus 35 times 81 divided by 59. And then we're going to bump over here and multiply by the final square root, which is 1 divided by 25 plus 1 divided by 36. So the entire margin of error, if you're working this out, reduces to 3.8633. 3.8633, which we're going to add and subtract to the estimated difference to get the lower bound and the upper bound. So negative 10 minus that is going to be 6.1367, I think. Oh wait, now we're going to subtract. That makes it negative 13. Sorry, I did the other way. 13.8633, and then the upper bound is what I said it was. We got negative 10 plus that. Yeah, that's pretty close. Negative, come on, there it is. Negative 6.1367. Okay. And you can see that this is in agreement, even though we changed the method of computing the margin of error, the standard deviation in the margin of error. This is still in agreement with the previous result, which is no surprise considering how significant it was. The hypothesized difference, mu1 minus mu2 equals 0, is outside the interval. The interval lies entirely below that. So this is evidence, we can say with 95% confidence, the true value of the difference lies somewhere between negative 13.8 and negative 6.1. And that's how you do it. So I think I've ran out of time here. I did a little bit more than an hour, and the peanut gallery over there wants to move on. So, oh, he's winning now. Okay. Oh, I can do it. I'll do another example. I'm going to do the paired t-test.
Excellent.
And I'm going to start throwing chalk at him. Whip it. I'm going to whip the chalk, and if you're not nice, I'll whip the chalk brush at you. Okay. So I'm going to wing this, but that's not hard. It's going to be the first time I kind of just sort of threw it at the wall and let it stick. That's a spaghetti reference. Okay. Let's talk about the paired t-test. So this is one of the first, maybe the only instance, I think, in this course where we deal with dependent data. And I'll give you a rough illustration of how it works out here, since they're playing video games over there now. The whole idea is the participants in a paired t-test have at least two measurements. It falls into the heading of multiple or repeated measures statistics, but in this course, you've usually got a before and after. So every subject in the course, every subject in the study has two measurements. And what we're interested in is the statistical analysis of the difference of those measurements. Typically, this would be people who get rewrites on their exams. So, and that was one of the online questions for the homework too. So we have a prior and an after. So a priori and a posteriori. Hey, I know Latin too. After. Okay, so these are exam scores. We're just going to do a ridiculously simple example here. So let's use 4 exam takers. Okay, let's say the scores before were 50, 61, 42, and 38. So really only one person really passed the course. One got 1 on 50, 2 people failed. So the instructor felt sorry and said, okay, you guys can have a rewrite, but make sure you pass this time. Now, afterwards, we get 55. We get 52. What happened there? Who knows? This is 51. And Buddy just cratered. Okay. So here's before and after. Now, those aren't the numbers we use. And you may be led astray on the exam because sometimes data like this is presented in a summary table with 3 rows. Oh, we got a cat visiting us. Who's that? What's little boy? Mini cat. So the thing is, when they present to you a table of sample 1, sample 2, and then the 3rd row says differences, you're never using all 3 rows. You use the first 2 rows if you're going to conduct a 2-sample comparison. If you decide that the appropriate test is the paired t-test, then you use the 3rd row. But don't try to use all 3 at once because you can't. There's more numbers and there's places to put numbers. So the numbers we want to analyze then, we're going to go prior minus after. So 50 minus 51, negative 1. 61, what am I doing? Oh yeah, we're doing it that way. 61 minus 52 is 9. 42 minus 51 is negative 9. And 38 minus 25 is negative 13. So what we need is y bar of the differences. On the formula sheet, it's labeled as d bar for differences. We'll get to that in a minute. We need s sub d, which is going to be the standard deviation of the differences. And here is 4. Well, you'll notice these two cancel out. And this makes negative 14. And that's a terrible number because it doesn't divide nicely. So the average is negative 14 divided by 4. So negative 14 divided by 4 is negative 3.5. That's not too bad. We can work with that. What's the standard deviation of that? I know my calculator here. Let's just do it. because if you're going to work this out yourself, I don't want you to be going, well, Erickson just threw up some silly ass numbers and nothing makes sense. So we're not going to do that. It's really easy actually to, with a calculator, to get the standard deviation. So let me do that. I guess we got to go find it first, don't we? Sample standard deviation is the one we want. There it is. We need a list, so we select list, and we have -1, 9, -9, and -13. So sample standard deviation is 9.7. Good enough for me. We're not going to chase a bunch of decimals around here. So this is 9.7. Well, guess what? Now all this complicated nonsense reduces down to a simple one-sample t-test. The null hypothesis will be that the mean of the differences is unchanged, 0. And we're going to go with the alternative hypothesis is that the mean of the differences is not 0. So that makes it a two-tailed test, which means we need to be very careful with the p-value. Typically, I would say remember to multiply the p-value by 2, but the t-tables that you're using have two-tail probability on them at the very top. Just going to read it off that. Now, what's the formula? T, degrees of freedom, is n minus 1, so df is 3 here. We're going to have d bar minus mu sub d over s sub d and square root n. So mu sub d is just 0. Our average was -3.5. We have that. Standard deviation of the differences with 9.7. And the square root of 4 is 2. So our test statistic on 3 degrees of freedom is about to come flying at us with vigor. So we have -3.5 divided by 9.7. And, oh, I screwed that up. My bad. I forgot to open a bracket. Whoops, that's a vector. We get 9.7 divided by 2. And we get -0.722. Nope, 722. So here we have, whoops, wrong color. -0.722. That's our test statistic. And you're thinking, how could the test statistic be that small? Given the size of the difference and everything. I mean, this is -13. We got -9. It's because our sample size is only 4. And we don't have a lot of information. So it's highly variable. If we had done, let's say there had been 10, 15 of these observations, any of these pairs, we would have probably had a much different result. But this is just a simple example. So there's nothing significant about this. So I'm not even going to give you the p-value because it's very large. So what happens on the t-table if the test statistic you're interested in evaluating isn't in the range of values they give you? So what you're going to do is you look at the appropriate row. So here would be row 3. And you'll see that the test statistic, remember we use absolute values, so, well, you need to choose the test statistic on a question that asks for it with the negative sign. But when you go to the t-table, you throw the negative away. So what you find here, well, let me draw a picture because they're still wrapping over there. Okay, so what I'm getting at, let's make some room here. So this rectangle represents the given values of the t-table. The largest p-value for 2 samples is 0.20 or 0.10. I shouldn't say for 2 samples, for two-tail probability. We got 20% in the far left column, and then all the way on the far right, it's either going to be 0.01 for 2-tail or 0.005 for 1-tail probability. Now you ask yourself, where on the appropriate row does our test statistic fall? So the appropriate row here is row 3. So this is DF3. Well, 0.722 is on the left margin So all you can say about the p-value for a test statistic of 0.722 and 3 degrees of freedom is whatever the p-value is, it's greater than the biggest p-value on the top of the table. Now remember, this was a two-tail test, so we're using the top row. The p-value, whatever it is greater than 0.020. And clearly, we failed to reject the null hypothesis. Now, let's say the test statistic was 17.22, some ridiculously large number. Well, the ridiculously large numbers are over here on the right. So I'm just going to make up a number, like I said, 17.22. So that is far larger than the largest number on row 3, so we're off on the right-hand column. And all we can say then is that the appropriate p-value is less than the appropriate value up here. Since this is a two-tail test, whatever the p-value is, it's smaller than 0.01. If it was a one-tail test, we would say the p-value is smaller than 0.005. You know, guys, we had like 8 people there for a while. They were waiting for you.
Ready.
He's ready. He's doing well on Mario. So this is how to read the table. Now, could do a confidence interval for this, but it's the same as the one sample T confidence interval. Do I have enough time here to talk about some more stuff, maybe? I guess I do. Okay. I had to go look at the peanut gallery. All right. What's that?
So do you want to do some regression stuff?
No, not really.
Okay.
But what I was going to do was maybe talk about how to do interpolation.
No, we're doing DMX. Move, get out the way.
We're going to talk about interpolation on the Z table. I don't have one in front of me at the moment, but I'm going to use some numbers that I do know from the top of my head. And this will be of assistance to you. So what I will do, this is, I'm going to, are you, oh, you are here, okay. I was going to do an interpolation, but I'll save that for another day. Okay, so any coffee left, or you guys drink it all?
There's like, the dregs, I guess.
Okay, well, you know, sometimes that's all you get. Are you doing chalk or are you doing whiteboard?
Let me touch your boobs.
No, you ain't touching that.
I asked.
No, you can ask all you want, but you ain't doing it.
Lorenzo wouldn't sit on my lap either, so.
Well, that's Lorenzo.
Here, damn it.
He's here to run the show. I'm just the dance. There's lots of coffee left, yeah.
Okay, so I'm going to go get a coffee. Be nice to him. He's had a hard day. You know, with the Mario beating him up and everything.
I just won Mario, so.
Oh, you did? Okay.
What are we doing? I don't even know what I'm doing. I was just like, I'm ready now.
We'll do some problem solving. Some more integrals, maybe. Some more linear algebra.
Want to do integrals? He suggested 2 things. I'm going to do neither of those.
Excellent.
I was just talking to myself out loud.
You normally talk to yourself in
When I talk to myself, I prefer to be alone, but okay. We talked about random thoughts of a wizard a few times ago, unless we start getting, but now there's 4 people here. We talked about non-linear, so let's do that, versus, I know Latin too, versus linear, versus linear Diophantine equations. Oh, you can't hear it. Tim probably can't hear the Mario, but I can.
Did I hear my name?
I just said I can hear the Mario, but you probably can't.
Oh, no, I can't actually. I can say, what are you talking about?
All right, so in this case, if you wanted to do, you could do weighted ones. They also have this at the end of one of the books I was looking at, weighted Pythagorean triples. versus this guy. So if you look at that, the ones that we're doing normally, classical Pythagorean triples are A is 1, B is 1, and C is 1. But then you could do this without less of generosity. You could probably divide by one of these and then have at least one of these always be monic. But this one was non-trivial. What we ended up finding was if you take p squared minus q squared 2pq and p squared plus q squared, where 0 is less than q is less than p. These are called primitive Pythagorean triples, but this still doesn't get all the Pythagorean triples because, or the rational ones, because you could multiply by d where d is irrational. So if you think about this as an ordered pair, you could put that in there. But you can prove as a theorem that these are all the rational Pythagorean triples. Again, in general, what you're doing with this is you're saying that this is x classically, y and z, and then if you have a right triangle, which is pi over 2 radians, because we're not going to use degrees here, this gives us, you can do a lot of these. The two special ones that you get are the unit isosceles right triangle, where the hypotenuse now would be h squared is equal to 1 squared plus 1 squared, which is 2. And then we're going to call it h for Hypaepus, who they drowned after he proved that root 2 was irrational. What that means is if you do that, it's going to be 1.414. It's almost a half. So if you take this unit length and then lay it off of there, there's no unit that you could find that would actually give you integers on the diagonal. So this is called the fact that root 2 is irrational is the same thing as saying that, and also you could make a square from this, the diagonal of the unit square is incommensurable to either of the sides. It's sides. I don't know why I had to write that out, but this is what they're saying in old, where we get the pi also. Pi is also another ratio. This is a tangent now, but pi is, if we call this circumference and this the diameter, that is the ratio. So this irrational number and root 2 are the two classic ones. The other one that we can do before we start the versus tangent of a tangent is we get irrational numbers not by trying to torture first year students or trying to torture us. It's from geometry that you get all these irrational numbers. So pi is the constant ratio to circumference and diameter in any circle. And then you get root 2 is another guy that you're going to get from this. And then another one you can get is root 5. But the best way to do that is start off with the unit right triangle again. Let's do it slightly slanted. Which way is it going to go? Is that okay? Yeah, let's do it that way.
Looks good.
I was going to draw from there. So this one's root 2, right? You believe me? If those are ones and ones. And now what nature does to build this shell, I think I did this once before, is erect a perpendicular, which you can do in geometry, and then make it and then cut it off of unit length, and then draw this. Erect a perpendicular, and then draw this. Erect a perpendicular. I said perpendicular. Perpendicular. Pickle Rick. Where is that giant Pickle Rick? Upstairs. And then erect a perpendicular, and then cut it off. Erect a perpendicular, and then cut it off. Erect a perpendicular, and then cut it off. If those are all, nature doesn't do it exactly either, but erect a perpendicular and do this. So you're going to get the shell. And then what's nice about that is you get root 3, root 4, root 5, root 6, root 7, root 8, root 9, which is 3. So you get the integers and all the irrational numbers, the square roots of numbers from geometry, and nature are building these.
Spiral of Theodorus.
Yeah. Or the other way to do this is to take, can we do this? We'll do it on another one, I'll cheat. But can you take this and cut this? This is the definition of the golden ratio. If you call this, usually I call this one x and this one 1. So if you have a unit length 1, it doesn't really matter. But what that's going to say is the ratio, the golden ratio is, can you take a segment and cut it with one cut such that the whole segment to the larger segment is equal to the ratio of the larger segment over the unit length. And then if you want that, it will involve root 5, which means it's also going to be irrational. And this is where we get random thoughts of madman, or the fact that, can you show that the golden ratio involves root 5, and then that would have to be irrational. So what are we going to get from this? What we have is, if you bring this up, we get x squared minus x minus 1 equals 0. So now I have a quadratic from this ratio, from this divine proportion, which is what Leonardo da Vinci called it. If you now take this, what do I have to do? B is negative 1/2 divided by 2, or negative 1 divided by 2 squared. So I need 1/4. So I need 1/4, but I'm going to add in 0. So I have x squared minus x plus 1/4 minus 1/4 minus 1 equals 0. This is the completed square. That's going to give me x minus 1/2 squared equals 5/4. And there it is. There's the golden ratio. So that's going to tell me that x is equal to 1 plus root 5/2, which is the golden ratio, or x is negative root 5/2. And why is this an irrational number? So then you start, so what I'm showing is geometry is going to push a lot of this, and this is where we get mathematics from, is nature and certain ratios. Euclid called it the extreme and mean ratio, the extreme average ratio. Da Vinci called it the divine proportion. In Italian, it sounds like something else. I've got the book somewhere, but he put it in the Vitruvius Man. If you look at the chest, he puts the golden rectangle in there. So if you cut this now in the golden ratio, and then if you erect a perpendicular and make the square from that, each one of these is going to be the golden ratio. And then you can do it again, then you can do it again, then you can do it again. I'm cheating because I have this. Now if you take the outside points here, it will create the same thing. And then that's what I tattooed. So this is the divine proportion and the golden spiral, they call it often, the golden spiral. Gauss had a quote on that. There's the two major things that are in here that are that he called it equivalent to the finest gems and solid gold. One was our Kepler might have done this. I don't know who said it, but one of them is the golden ratio, and the other one is pi, the ratio pi, I believe. I'm going to have to find the quote and put this up. But the point is, all of these things in this number theory all starts from looking at geometric considerations. Why I also like this one is, if you do this again and you create the golden ratio, each one of these rectangles is the golden rectangle. So this one is the golden rectangle, but this one also is a smaller golden rectangle. If I do it again and create the square here, you also get areas which are going to be larger and larger. So you're going to get the Fibonacci. The area is the Fibonacci numbers of each of these sub squares. So you can get 1, 1, 2, 3, etc., etc. But more importantly, when I do this, if I want to, now let's use a different color, I can ruin art for you. Now I have a road, a road, and if I'm doing that, it's like, I don't think they had dividing lines because they weren't using the Autobahn. But the point being is, now if I draw a person in the foreground, he's got no legs. I have no legs. There, now he's got some legs. So he's trying to straddle that. And then if I draw a person in this background here, each one of these is the same rectangle or golden rectangle. So it's a perspective preserving vanishing point, or a line of vanishing. So in geometry, also when they did the big Fresnos, like when Michelangelo did this in the Vatican, when it's done. But when the big Fresno start going off kilter, they would use the golden spiral to bring it back. So then it would slow. They would draw the golden spiral and then start drawing it back, and then it would correct their errors in this. So this gives perspective preserving vanishing line. So if I draw the guy in the foreground and in the background, they're going to have the same perspective because each one of those rectangles is the golden rectangle, so they all have the same proportion, the divine proportion. The divine proportion. I forgot what I was talking about now because I got tangented on this. And then what you would want to do, let's talk about that then, I guess, before I talk about this. What I was going to do was solving all of these non-linear, it's like now I'm going to start sneezing again because it's like I have to do this, but this is the way you have to do it. On the blackboard, your hands get white. On the whiteboard, your hands get black from the ink. This is the way it goes.
Need more coffee? Is that what that?
Don't shake your drink at me. It's at the bar. It's like, don't shake your drink at me. Just a second. I can get one. I'll run out, dip out, dip in. So a lot of the numbers, the square roots of all these numbers, root 2, root 3, root 5, etc., and then pi, and then e comes along quite a bit later because we need him from calculus. These are the first types of name. There's infinitely many, uncountably infinitely many more rational numbers like 1/2 and 3/2 and 5/2. I like 5/2 because both in his decimal expansion and his fractional form he has the same two numbers, 5/4. Yeah, you forgot 1/2 of my concoction. Stop. Where's the cream? Cream, dollar bill, y'all. Now we're gonna sing Wu-Tang Clan. Wu-Tang Clan, Tiger style, Tiger style. All right.
Hell yeah. Wu-Tang Clan ain't
Nothing.
nothing.
I was gonna say that. Give me that. I'm driving. You won't sit on my lap. You don't get to pour my cream. What? Exactly.
Whoa,
Exactly.
whoa. Let's back that shit up.
What he said. Here, just wait. Now I gotta.
Oh, just, yeah, what are you doing?
Whoa.
I'm giving it to Tim.
Oh, okay. Thank you.
What was I talking about? So we have all these irrational numbers. There's infinitely many, uncountably many more. If you take the real numbers, then you can just draw over here the rational numbers. And then they didn't even give it a symbol, the complement of the rational numbers. We won't get into the transcendental numbers. But every real number can be viewed as, intuitively speaking, if we're not going to use Dedekind cuts or Cauchy sequences, Q is the set union of rationals and irrationals. And why can this be? You can prove that every number has an infinite decimal expansion. Either it repeats or it doesn't repeat. So if you have repeating, you're rational, you can prove. And then if you're non-repeating, you're irrational. I was going to tie that into some. Oh, and then what we would get from this is you want to get weird statements and a bunch of number theory things, but it seems a whole lot more useful if you know where I'm going to try and get these things. I want to now prove, say, that the golden ratio, 1 plus root 5/2, is irrational. Okay, how would I do that? Do you want to just do it in real time? Let's use reductio ad absurdum. I know Latin. And prove this. So what you would do from this and why you would want to do this, it starts to show the motivations. Oh, and put that in the wrong spot. Either it's going to go, that's an anima. Either the table or the coffee is going to go up my butt if I put it there again. I'm going to move that eventually. But here's a statement we would get. I want to prove that this is irrational. And what I'm going to view it as 1/2, which is rational, times 1.5. That also bothers people. So the first statement is, if you take a rational number, which is going to be 1 in this case, and an irrational number, can you prove that their sum is irrational? So first I'm going to prove that 1 plus root 5 is irrational. Yes. So I use reductio ad absurdum. So this is proof by contradiction. And so what would I do? I would say that, first of all, I have to show that this is closed under addition. This is a field in and of itself, so I'm just jumping into this. But this is closed under addition and multiplication. So what that means is if you take two rational numbers, you get another rational number. If you add two rational numbers, you get another rational number. So now using that fact as a wave of the hand, if I assume on the other hand that P plus Q is in Q, and this is also the definition of divisibility, but that means that there exists an R, say, inside Q, such that their sum equals that. Because I'm assuming it's rational, so there has to be one. But then what do? R minus P. I subtract P from both sides, which I'm allowed to do, which is R plus negative P. But I've said that this is closed under this. So this says that Q is now rational and Q is irrational, which is a contradiction. Therefore, this can't be true because I've a priori assumed that Q was irrational. I just proved that if this sum is rational, then Q has to be rational and irrational at the same time. And no number can have an infinite repeating expansion and a non-repeating expansion. So this guy can't be rational. So the sum of any rational number and irrational number is irrational, which means 1 plus root 5 is rational or irrational. Now I'm going to do another theorem that says, now that I know that 1 plus root 5 is irrational, I want to know if I multiplied by 1/2. If I take a rational number and an irrational number, that has to also be P times Q has to be irrational. Proof. I use reductio ad absurdum again. If I assume that P is rational and Q is irrational and P times Q is rational, that means there has to exist an R such that P times Q is that rational number. But why is that a problem? Because now I have Q is equal to 1 over P times R, and because I have closure of multiplication in Q again, this says that Q is both rational and irrational. Therefore, this is a contradiction again, and so the multiplication of a rational number times an irrational number is also irrational, and that proves that the golden ratio, which is 1/2 times 1 plus root 5, has to be irrational. So the golden ratio is not a rational number. But this drives the importance of this because this is the golden ratio, the divine proportion, or the extreme and mean ratio, which we can show in another time, which I did in a Torus talk. On how to construct the golden ratio with a compass and a straight edge. That's for another time. So my point being is we get these numbers and a bunch of these types of things from geometry, and most of the time the two important ones are 1, 1 and root 2, and that gives you your trigonometric identities for the unit circle, and the other one is if you use 2 and a 1 and a 2 here, then this one has to be root 3. So, and most of the time when you have a right triangle, if two of them are integers, it doesn't mean that the third one is an integer, and that's where they started getting the game. The only way I would have this is the 3, 4, 5 is the first integer one, because if I have 3 is less than 4, then that's the or is that the 1 less than 2? P squared minus Q squared. Yeah, 1 is less than 2, which is the P and the Q. If I use 2 squared minus 1 squared, that gives me 3. If I use 2PQ, that gives me 2 times 1, which is the 4. And if I use 2 squared plus 1 squared, that gives me the 5. So that's the first Pythagorean triple. The 3, 4, 5 comes from the primitive where I'm assuming that Q is positive and less than P. That's the first one that you get. So this is what they started doing. They started noticing that there's the 3, 4, 5 triangle, but in general, the hypotenuse or one of the other legs is not always rational, because root 3 is irrational and root 2 is irrational. You can prove that these are also true using reductio ad absurdum. Do you want to see that, or do you want to keep going with that? How do I know that root 2 is irrational? Well, you can do this for any prime P if you really want, but the best way to do that is, again, I use reductio ad absurdum. Okay, so I'm using reductio ad absurdum, which means reduced to an absurdity. I don't know why we're using orange. Orange on black, Halloween, spooky. So what I do is I assume that it's rational. And so what I do is I want to say that it's m over n where they're in lowest terms, which means the GCD of m and n is 1. What that means is there's no numbers other than 1 that divide both m and n, and that'll be my contradiction. So what do? Square both sides, and I get 2 is equal to m squared times n squared, which means that 2n squared is equal to m squared, which means 2 divides m squared. And then if I use Euclid's lemma, this says that 2 divides m. If 2 divides a product, m times m, and 2 is prime, then 2 has to divide one of the products, in this case either one, so 2 divides m. But if that's true, then that means that m is equal to 2k. So then m squared is equal to 2 times k squared, and I put that into here. And then I get 2n squared is equal to 2 times 2k squared. Cancel, cancel. But what does that say? That says 2 divides n squared now. And by Euclid's lemma again, this says that 2 divides n. But I assume that the only thing that divides m and n is 1. And I just showed that 2 divides m and 2 divides m. So that's a contradiction, because I've said that their GCD now has to be, this says that the GCD of m and n has to be greater than or equal to 2. It might have something larger, but last time I checked, 2 is strictly larger than 1, so this is the contradiction. I've said that the GCD is exactly 1, and then if I assume that this is rational, I get that the GCD has to be strictly larger than 1 and equal to 1 at the same time. This can't be true, so the square root of 2 is also prime, or irrational. I don't know where we're going with this. I just started, and then we're going. But this is, geometry is driving all of this. And then now, what was I going to do? Something, right? Chew.
You could always do root 2 to the root 2. Is it rational?
Yeah, I know. I don't know. Is pi to the root 2. You should appreciate your calculator. It's truncating it. How do you do that? How do you approximate pi to any of these things? It has to be rational numbers or exponents. How do you do even 2 to the root 2? How do you multiply a number by itself root 2 times? That's where I was probably going to go next. So I guess we're not doing the linear versus nonlinear anymore. We just turned into this. How do you actually compute this? You can't ever compute this. You could also have to argue eventually why this would be rational or irrational. I don't know the argument, but if I want to approximate this, what I do is this is approximately equal to 2 to the 1.414, which is approximately equal to 141 over 100 if I want this. And then now that's the 100th root of 2 times the 141. So I know how to compute this and then this. So I turn it into rational approximation of irrational numbers. Even in the exponent is how I would approximate this number. You should probably appreciate your calculator. That's not where I was going to go with this. I just lost it again where I was going to go with it. I was going to go to... I was going to go somewhere. Hell, probably, but not today, Satan. Oh. Not Tim's Babylonian method of approximating. How did I know that the root 2 was approximately 1.414? So I had to draw this big. Usually they would say you need an initial guess. How do you do the initial guess? My number n is 2. I find the perfect square on either side of this. So last time I checked, 1 is less than 2 is less than 4. Let me check again. Yes. Now I take the square root. That says that 1 is less than the square root of 2 is less than 2. So the square root of 2 is somewhere between 1 and 2. 2. Those are my first guesses. This is x naught and y naught. in each time the X and the Y naughts are going to flip roles. They're going to get smaller and bigger as I do this back and forth, but it doesn't really matter. On an exam, I'll tell you when to stop. I'm not going to do this. This doesn't converge exponentially. It converges fairly slowly. There's better ways of doing this using Newton's method of approximation, etc. But Andy Liu used to call this the Newton, but it's the Babylonians that did this first. They have a pretty good way of doing this. What they did know is, and can you prove this, I guess, they make you do this in the appendices of Stewart calculus, but once I have the Cartesian plane, what's the average of the midpoint of a number? It's the average, statistical average of the two numbers. So the exact midpoint of this will be 1 plus 2 over 2, which is 3 over 2. So if I know now, why is that useful for us? Well, if I know, is that half? How do you bisect a number? Okay. Oh, that was okay. That's the bisecting. So I bisected it in half using a compass and a straight edge, my arm, roughly speaking. But that's how you find a perpendicular bisector of an interval. And so this line would be 3 over 2, the average of it. And we know that the actual value of square root of 2 is going to be slightly less, 1.4, not 1.5. But do you see, these were my initial guesses for it, x0 and y0. And so now how do you get a new x0 guess, which is better than that? I'm going to call in each step, x1 is going to be x0 plus y0 over 2, the average of the previous guess. So that will give me 1 plus 2 over 2, which is 3 over 2. And then this one is going to go round and round. But what's going to happen? We're going to say what's y. What we're doing in each guess is that y1 times yx1 is exactly equal to 2, that they're both the square root of 2. So then I can find the other guy for free. That's just going to be 2 over x1. And so what that says is, what is that? That's 2 over 1 times the divided by 2 over 3. So that's 2 over 3, which is 4/3. 4/3 is what? 1.3 repeating, if you know how to do that. So now what we did was we just showed that somewhere we now know that x2 was 1.5. That got really small really fast, you see. Now I have between 4 over 3 and 2/3, the square root has to be lying somewhere in between those. I won't draw it on the picture anymore or start blowing that up. And then now what do I do? In the next step, I would guess that x2 is going to be what? The average of these two. If I take the average, I'm going to get closer to it because it'll always be in the middle of that. So that's going to be x1 plus y1 over 2. My previous guess was this is going to be 1/2. And it's like, why do I want to know how to add fractions to approximate this irrational number? So I'm going to get 1/2, the division by 2 times what was this? x1 was 4/3 plus 3 over 2. I need a common denominator, so this one's missing a 2, so I multiply by 2 over 2 and 3 over 3. There's a pattern here that actually happens because it's going to be what? 8 and then 3 squared, so this will be 1/2 times 8 plus 9 over 6, which is 17 over 12. And then what's the next guess? y2 is going to be equal to the number n over x2. So let's do this now. This became 17 over 2, 12. Meow, meow. I hear you. Oh, we lost Purple. Meow, meow. I don't think anyone else can hear you. Come down here.
He just meows to himself every so often.
Kitty. I know. So that what we're doing, we're computing these numbers here for you. And then so now this is going to be 2 over 1 times 12 over 17. I know, get over that, which is 24 over 17. They flip their roles. That's how I know they're bigger and smaller. And now in that guess, let's see how we would do this. I guess I'm going to do both because we're on stream and we're going to end it on a high note. But now what do I want to do? Here's the trick that they never showed you to do when they do long division. I have to do 17 divided by 12. and I have to do this one after. So the way you want to do this is put 0, 0, and then we're going to find the decimal expansion. And how do you know in each step which are the correct? Oh, you're empty. It got me. Almost got me again. I knocked it over. I know, Kitty. What was that? Kitty, 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 kitty. Let's put your war paint on. No, go bother them. Yeah. Psh, psh. Kitty. I swear there's a cat. Yeah, there he is. My cat says, psh, 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 psh. Tell my cat, he says, psh, psh, psh. So list the multiples of 12 first. How do you do that? Just add 12 to itself a bunch of times. I'm going to go to 4 because I know that that's the answer for 1.414. But just keep adding 12, and then what am I going to get? I got to start adding. 48. This one's going to be 60. How many inches in 5 feet? 60. But why have I done that? This is times 1. This is times 2. This is times 3. This is times 4. This is times 5. Okay? Now what I ask myself is, we know that it has to be what? 1 point something, because our first guess was the square root of 2 is less than this. So we already know that the square root of 2 has to be equal to 1 point something. Right? From the first guess. It can't be 2 point something. It has to be 1 point something. So, and it shows us this. So if you're doing any justice in the world, what that says is, how many times does 12 go into 17 without going over 1? And then I get 12. I subtract. I get 5. I bring it down. And now I ask myself, what's the closest multiple of 12 that doesn't go over 50? I've already got it listed. So it's 4. And then I have the answer already. That speeds up long division drastically for yourself. Then I subtract, I get 20. And then what's the closest multiple of 12, which doesn't go over 20? It's 1. And I get 12, and then I get an 8. And then I bring another 0 down, and I say 80. And it's like, okay, well, crap. 12 would be 72, and then 12 would be what? 84. So it's going to be this, which is the wrong answer, but then we'll see. So what was it? It was times 6. And then how do I know which of these digits are correct? You ask yourself, oh, ha, ha, ha. Now what we're going to do is we're going to divide 24 by 17. And then that one is a lot less trivial. So I want to do 17. 17 plus 17. Uh-oh. Tim. 34. 17 is going to be 151. 17 is going to give me 68. And then 7. I've done this before. That's the only reason I'm this fast at it. Same as Tim. Oh, but Tim might be good at it. What is that? 85. So I'm going somewhere with this. What should it be? 17 should be 1 again. Uh-oh, Tim. Borrow. 14. What does that give me? Crap, I don't know. 14. I was working it out. I'll take it. 70. Now, how many times is 17? Now, do you see what's the closest multiple that doesn't go over? Oh, 4, which is 68, and then I get a 2, and I get a 20, and it's going to be a 1, and that'll be 17. This will be 30, and then what do I get? 17 goes into the 30. Oh, 1 again. So now I know, because if I take those numbers, 1.414, which I knew was the larger one, and then I take the other estimate, this was x2, and then y2, my guesses, will be 1.411, and I subtract those. Where I get zeros means that those are the correct digits. As soon as I get a non-zero, those were not the correct digits. So to 2 places, the square root of 2 is 1.414, 213, Hey?
I say now do it with linear approximation for the calculus people.
Oh, what? But I need a perfect square on that, don't I? How am I going to phrase that?
Like Newton's method? Or
No, linear approximation. 1's a perfect square. That's pretty close.
You think? Well, let's see which one gets us better. So let's call f of x the square root of x, you're saying then. So what he's saying is f of 1, you have to find in linear approximation, you have to have an a value which gives you something where you know how to compute it. So I get 1, check. So near, let's put that in quotes for sure now, near 1, we know that What is this going to be? This will be LA of x, not the airport in LA, but the different guy, LAX. This is going to be L1 of x, which is what? It's the equation of the tangent line to that curve at 1. So what's that going to be? That tangent line? It's going to be LA of x in general is f prime of x, f prime of a, x minus a plus f of a. How do I know that this is the formula? It's that formula because what do I know? I have a point A, f of a, and I know the slope of the tangent line is f prime of a. So now if I use the equation of the tangent line, or the point slope form of this line, this should be y tangent minus f of a equals the slope of the tangent times x minus a. If I put that in there and solve, y tangent is f prime of a, x minus a plus f of a, which is exactly this. This is not a new formula. I don't know why they don't just do this right next to it. The linear approximation is the equation of the tangent line. They're the same. I just use a different color. Let's use a third different color. Now let's do that for our function. We did this, they made me do this yesterday twice when I had to do the Lagrange multipliers, but the square root of this guy, f prime of x, is equal to 1 over 2 root x. Don't memorize this formula. What you want to do is turn that guy into 1/2. You bring the exponent down, 1/2, subtract 1, you get a negative 1/2, which is this guy. At 1, that's going to give me f prime of 1 is going to give me 1/2 square root of 1. So now what that says is L1 of x is equal to 1/2 times x minus 1 plus f of 1, which is 1. Where was I now? Now I want the square root of 2, which is f of 2, which is approximately equal to L1 of 2, which will be 1/2 2 minus 1 plus 1, which is 3 over 2, not even fucking near mine, which was my first guess in the Babylonian approximation. Newton ain't got crap, or the Babylonians, Newton ain't got crap on those Babylonians. I had to say it right.
It's almost like you should do a history of math or something, because that was a great.
Let's do history of math in a pod. We should do a podcast form.
Okay. Oh my God, what an idea!
It has to be a video podcast or something like this. We lost somebody when we did that. So I'm going to sneeze right away anyways. And then, so let's segue. Next time what I was going to do was use the Euclidean. I already did that, didn't I? Did I use the Euclidean Bezuian algorithm to find the solution? Yeah. Okay, good thing we did that tangent. Otherwise, we'll repeat it. If I repeat myself, take it as a win. I think that's it for today. I got to go get groceries and a bunch of crap.
Yeah, that's good. We'll be sure to do a history of math podcast, video series, something or other, lecture.
Yeah.
Something like that at some point. But thank you, everyone.
Thanks for showing up.
Yeah.
Tim towed the line today. I just talked about random crap.
Right on. All right, everybody. Goodbye.
See it. Tim, come and touch my boobs.